In this video, we're going to talk about linear quadratic systems. A linear function and a quadratic function can intersect at 0 points, 1 point, or 2 points, and these points of intersection can be found graphically or algebraically. And today we're going to focus on algebraically determining points of intersection. So just as a quick note, two quadratic functions can also intersect at 0 points, 1 point, or 2 points. And if the two quadratic functions are identical, then two quadratic functions can intersect at an infinite number of points. So let's first look at the linear function and the quadratic function. We can see perhaps intuitively that a parabola and a straight line might intersect at 1 point or 0 points or perhaps at 2 points. Similarly, two parabolas might never intersect, or they might intersect at precisely 1 point, or they might intersect at 2 points. And we don't necessarily know. And it's also, as mentioned, it's possible to have the same parabola written twice, in which case you see that they would intersect at an infinite number of points. Okay, so what if we were asked to determine the points of intersection between the parabola shown and the linear function shown? Well, what we would do is simply let the y value of the first equal the y value of the second. So we would get 3x squared minus 10x minus 100 equals negative 4x plus 5. We would want to make one side equal 0. So algebraically, we could do that by writing 3x squared minus 10x minus 100 plus 4x minus 5 equals 0. Ultimately, we would get 3x squared minus 6x minus 105 equals 0. Common factoring out the 3 would give us x squared minus 2x minus 35 is 0. And ultimately, we would get 3 times x plus 5 times x minus 7 is equal to 0. So that would mean either x plus 5 equals 0 or x minus 7 equals 0, ultimately meaning either x is negative 5 or x is 7. Okay, now to determine the points of intersection, we need to take those x values and plug them into either of the functions to determine the y values of the corresponding points. It doesn't matter which of those functions we sub it in. So since we have a linear function g of x equals negative 4x plus 5, we'll simply sub in an x value of negative 5 and an x value of 7 to that. If we let x be negative 5, then g at negative 5 equals 25, meaning one of the points of intersection is negative 5, 25. If we let x equal 7, then we see that g at 7 equals negative 23, meaning one of the points is 7, comma, negative 23. And we have the 2 points of intersection of the straight line with the parabola. So that was obviously a case that, looked something like that. Now, what if we were given the parabola shown here and the straight line shown here? Well, to determine the points of intersection there, we would see that 4x squared plus 30x plus 30 would need to equal 10x plus 5. We're simply letting the y values equal each other. We would get all the x's on one side, ultimately meaning that 4x squared plus 20x plus 25 was equal to 0. Now, 4x squared plus 20x plus 25 factors to the quantity 2x plus 5 times the quantity 2x plus 5. So that would mean that 2x plus 5 would need to equal 0, ultimately meaning x was equal to negative 5 over 2, and there was only one point of intersection. So we could then take that x value of negative 5 over 2 and plug it into either of the original two functions. So we'll choose k of x equals 10x plus 5, subbing in the x value of negative 5 over 2, we get y equaling 20, and we see that we've got one point of intersection as shown down below. And so what that would mean is that we have a parabola and a straight line, and didn't draw it the best there, but they're intersecting at only one point. And then finally, what if we were given the functions shown below? Well, what we could do to determine if there are any points of intersection is simply, first of all, let's try to get this linear expression expressed as a function in terms of y. So what we'll do is reorganize, getting y on one side. We'll isolate the y by dividing both sides by negative 2, and ultimately we'll see that y is equal to 3 halves x minus 7. We'll then take that 3 halves x minus 7 and set it equal to the y value of the parabola in the first uh, function. So again, the first function is essentially y equals 4x squared minus 10x plus 38. And the second function, as shown here, is essentially y equals 3 halves x minus 7. So we simply set those two y values equal to each other and see if there are any solutions for x. So letting 4x squared minus 10x plus 38 equal 3 halves x minus 7. If we bring the 3 halves x and the negative 7 over to the other side, we get 4x squared minus 23 over 2x plus 45 equal to 0. Actually, what we did instead is we just multiplied the left-hand side and the right-hand side both by 2. And obviously we can do that. Then we brought the 3x and the negative 14 over, and we said 8x squared minus 23x plus 90 equals 0. And then we did our best to solve for x. We used the quadratic formula, and we saw that we got a negative discriminant. The value under the square root is negative. Well, therefore, there's not going to be any points of intersection. And so what we've got there is essentially a parabola and a straight line that never intersect. Now, another way we could have done the exact same question would have been to take the value of m of x and sub it directly in for the value of y in the line. So if you go back a while ago, we said the second function was 3x minus 2y minus 14 equals 0. And the first function was y equals 4x squared minus 10x plus 38. So all we're doing here is we're taking this expression for y and we're literally plugging it in right there. That will give you the same answer of no solutions, but it would work even if there were solutions. So doing that, plugging that y expression in, we ultimately get, again, 0 equaling 8x squared minus 23x plus 90. We get the same negative value for the discriminant. We see there are no points of intersection. Now, what if we had two parabolas as shown here, and we wanted to find out what are the points of intersection? So let's say we have the two parabolas and they have a couple of points of intersection as shown. Well, we don't only just want to know what are those points, we actually then want to know, using a little bit of grade 9 math, what's the equation of that straight line that connects those points of intersection? Okay, well, let's see if we can do it. We're going to take the first expression, x squared minus 7x plus 14, set it equal to the second expression, 2x squared minus 12x plus 8. And when we do that, we're going to see that ultimately 0 equals x squared minus 5x minus 6. Then we're going to factor that and get x minus 6 times x plus 1. And we'll see that either x is equal to 6 or x is equal to negative 1. Now we can take that x value of 6 and plug it into either the first or second expression. We'll get the same answer either way. Same with the x value of negative 1. So at x equals 6, we see y is 8, and at x equals negative 1, we see y is 22. And so we've got a couple points of intersection, one being 6, 8, and one being negative 1, 22. Now what we're going to do is go back in time, see if we can remember our grade 9 math, and find out the equation of the line connecting those 2 points. Well, the equation of a line is given by y equals mx plus b. So we can say that the slope will be y2 minus y1. And just to remind you, the points are 6, 8, and negative 1, 22. So we can say y2 minus y1 over x2 minus x1 is going to ultimately equal 14 over negative 7, which is negative 2. So instead of writing y equals mx plus b, we can write y equals negative 2x plus b. Now we can sub in the point 6, 8 or the point negative 122 for x and y. So what if we choose the point 6, 8? We can say 8 is equal to negative 2 times 6 plus b. So that would mean 8 is equal to negative 12 plus b, and ultimately that b is equal to 20. And so we'd be able to write that, not just that y is negative 2x plus b, but since b is 20, we'd be able to write y equals negative 2x plus 20 is the equation of the line of intersection that contains both points of intersection.